Hello again, and welcome to another review session for your final exam in Calculus 3208 presented by CDLI. And today we're talking about one of my favorite topics in calculus, which is related rates. I like it so much because it's so applicable in so many areas. All right, let's look first of all at some of the concepts we'll discuss today. We're going to look at the idea of what related rates of change are. We're going to talk about how we use implicit differentiation to determine, we apply that to related variables. So we find all kinds of different functions of time and also their rates of change as functions of time, how they're related to each other. It's neat stuff. Then we're going to solve related rates problems involving triangle scenarios. There's all kinds of different situations, as I said, that we can set up for related rates, and we're going to do a few different sessions on this. But this first one is just about triangle situations. All right, so let's get started. We'll talk about related variables. So here's a physical situation we'll start with. So you can read through that if you like. There's not much there to read. But basically all it says is we take a stone or a rock and we throw it into a very still pond. I'm sure everyone's done that at some time or another. And once you do that, you'll see it'll create some ripples on the pond when the stone hits the water. It makes a splash. So we get these wave patterns that sort of radiate outward from the place where the rock hit the water. So if you look at what's going on in this picture here, splash right here is where the rock hits the water, and then what happens is we get these kind of neat waves that move outward. And if we just sort of follow along one line, we can see that the radius of one of those circles as it moves outward will be expanding. So down here we're going to talk about that radius as one of the variables that we can look at for one of the particular circles in this sort of thing that's happening here. Something else we can see is that as one of those circles expands outward, the circumference of the circle, or the distance around its perimeter, will also be expanding. So the circumference is expanding, but it's also related to the radius. So radius and circumference are connected to each other. We should know that. Not only that, but the area of the circle, of course, is going to be increasing as time goes on as well. So each one of these three variables, the radius, the circumference, and the area, as the circle expands, can be thought of as a function of time, because as time increases, so do the values of each of those three important variables. Not only that, but they're all not only functions of time, but connected to each other. So each one of these things is related to each other, but they're all variables, which we can think of as functions, that are dependent on time. So we have three variables, each of which is a function of time, and all of which are related to each other. Now, related rates, what we describe those as, it's a situation when A, all the variables are related, and B, they're all functions of time. So here are the equations that relate them, and here they are written as time-dependent functions over here. Then, if that's the case, we say that their rates of change with respect to time are also related. So the derivative of the radius as a function of time is how fast the radius is changing. Well, since radius is a function of time, circumference is a function of time, and they're also related to each other, then their rates of change with respect to time must also be related to each other. Okay, and the same goes for area. So these three variables also have rates of change that are going to be connected if we think of those rates of change in terms of time. Alrighty, let's see if we can put some of this stuff together into some action here. So we're going to find the relationship between the rates by using implicit differentiation. So let's look at circumference and radius first. We know that circumference is 2 pi r. All right, if I want to find out how the speed at which the circumference is increasing compares to the speed at which the radius is increasing, well, I want to look at each one's derivative with respect to time. So I'm going to use implicit differentiation to take the derivative of this entire equation as a function of time. And so one way that you sometimes see that written out, actually, is you'll sometimes see folks say, okay, we'll call this c of t for circumference as a function of time, and that's 2 pi times r of t for radius as a function of time. So then the derivative could be c prime of t, of course, and 2 pi times something is just going to be 2 pi, if that's a variable. But remember, since radius is a function of time itself, we have to multiply by its derivative using the chain rule. So what we're doing here is we're using implicit differentiation with the chain rule. Now typically for related rates, we use the Leibniz notation for that, but it's the same idea. So the same kind of thing should go for area then. If I think of area as being pi r squared, both are time-dependent variables, then the rate of change of the area as a function of time should be the derivative of this expression, which is 2 pi r. But since r is also a function of time, we've got a function hidden inside there. We need to multiply by its derivative, which is dr over dt. Okay? So it's all about chain rule and implicit differentiation when it comes down to the actual mathematics of what's happening here. Let's look at what we can do with this particular example and see if we can figure some stuff out about an example that makes this a little more numerical for you. So consider the situation that we already described, and suppose the radius of one of the circles is expanding at a rate of 5 centimeters per second. So if the radius is expanding at 5 centimeters per second, what that tells me is that dr over dt, or the rate of change of radius with respect to time, is positive 5. You don't have to write the plus usually, of course, but I'm just emphasizing that. Then it says, how fast is the circumference expanding? So for part A, what we want to find is what is dc over dt. Well, we already saw this, but I'll rewrite it again anyway. We know the circumference is 2 pi r, and so using implicit differentiation and our chain rule, we know that dc over dt will be 2 pi multiplied by the derivative of r, which is dr by dt. Okay, so if I want to find out how fast the circumference is expanding, it's just going to be 2 pi multiplied by how fast the radius is expanding. So that's going to be 10 pi. And we could write it that way and say that it's going to be in 10 pi centimeters per second, because circumference has a linear measure even though it's a curved line. Or we could say, if we wanted to approximate that, that's going to be about 3.14 centimeters per, 31.4. Get that into there. Decimal's in the wrong place. Centimeters per second. Okay, in part B, it's a little bit trickier, but this is a typical thing that we see. We want to find out how fast is the radius expanding as a function of time. So what's dA over dt? Well, we already saw that dA over dt, since A was pi r squared, that dA over dt becomes 2 pi r times dr over dt using chain rule. So in this case, I can fill in what I know, but I don't just need the rate of change of radius. I also need to know how big is the radius at that time, because I need that extra information to solve this one. So the radius is actually 10 centimeters at that time, so I have to multiply that by 5 as well. So that's going to give me an answer of 20 pi centimeters per second as an exact value. And if you did want a decimal approximation, that's going to be about 62.8 centimeters per second. Okay? That's a very simple example, actually, but it's a good one to start with because I think it gives us the nuts and bolts of how we do this. So let's get down to some more realistic related rates. So here's an example. 2 planes leave Gander at the same time. One, not on, but one, forgot my E, typo. One is flying north at a speed of 150 kilometers an hour. The other is flying due east at a speed of 200 kilometers an hour. How fast are the planes moving away from each other 2 hours after they take off? Okay, that's a fun question. So what we're going to do is we're going to start with the dot right here. And that dot, ladies and gentlemen, is Gander. All right, so what we're going to do now is we're going to draw a line to represent the path of the plane that's heading north. And we're going to draw a line that represents the path of the plane that's heading east. Okay, and we'll give each of those a name. So the distance, and I'm saying distance, that the first plane is away from Gander, we can call it x. And the distance that the second plane has gotten away from Gander, we can call that one y. And then we're going to define a third quantity because they ask us how far are the planes, or how fast are they getting away from each other. The distance between the 2 planes at any given time will be that diagonal line right there. So let's give that one a name as well. We'll call that one z. Okay. So the information they give us, they tell us the first plane, the one that's going north, is moving at 150 kmph, and this one, the one going east, is 200. Those are actually derivatives. The derivative of x with respect to time is going to be how fast the length of this line right here is increasing, and it's going to be 150 kilometers an hour, so we'll call it 150. And dy over dt is going to be how fast this line down here is increasing in size, which is the distance we are away for the other plane, and that's 200. Now, here's the thing. We know that z is also a time-dependent variable. we need to find the relationships between x, y, and z so that we can find a relationship between their rates of change with respect to time. And you should have noticed that this is a right angle triangle, so we've got old Pythagoras again. So z squared equals x squared and y squared all put together. And now, in order to find information about rates of change, I have to differentiate this implicitly, not forgetting my chain rule. So the derivative of z squared is 2z, but using chain rule, we need to have dz over dt. And the derivative of x squared is 2x, and chain rule tells us to use dx by dt. And the derivative of y squared will be 2y, and chain rule tells us for that one we have to have a dy over dt. Okay, so a real quick simplification here, I can eat all of these 2's because dividing both sides of this equation by 2 make it nice. So let's think about things we have and things we want to find in order to solve this problem. Well, we already know what dx over dt is, and we already know what dy over dt is. If I want to find dz over dt, which is how fast they are moving apart, I need to know what's z, I need to know what's x, and I need to know what's y 2 hours after the planes have taken off. Well, that shouldn't be too hard to figure out, and this is sort of secondary information that I need to go back and put into my equation here. So if I go back and think about that now, 2 hours after the first plane takes off, if it's moving at 150 kilometers an hour, then its speed tells me I'm going to end up moving a distance 150 times 2 hours is 300 kilometers. So this is when time equals 2 hours. We're going to get some information here. The second plane, the one that's moving eastward, is moving at 200 kilometers an hour for 2 hours, so it's traveled 400 kilometers. Now, how far are they apart at that time? Well, if x is equal to 300 and y is equal to 400, Pythagorean theorem could tell me the length of z, or, as most of you have probably recognized, this is a simple Pythagorean triple. It's a multiple of a 3, 4, 5 triangle, but it's multiplied by 100, so we're going to be 500 kilometers for z. So all I have to do now is fill in all that information into my equation and solve for the required variable. So z is going to be 500, and dz by dt is the thing that we want to know, so let's leave that there. And that'll be equal to x, which was 400 for x, excuse me, times dx by dt, which we already saw was, jumping gee willikers, x is 300, isn't it? Getting my x and y's mixed up. Next will be my p's and q's. So that's 300, and dx by dt we already said was 150, plus y is 400, and we multiply that one by 200, which is how fast that plane is moving. So then, if I calculate all this stuff, I'm going to get that dz by dt shall be equal to 300 times 150 plus 400 times 200, and all that, I should make brackets to be consistent with my notation, yuck, okay, and all that has to be divided by 500. And so anybody who's really quick with arithmetic might be able to do that in their head. I'm going to punch it into my calculator here, so bear with me for 1 second. 300 times 150 plus 400 by 200 is a magic number that I'm going to divide by 500 and get 250. So it tells me that after 2 hours, the planes are moving away from each other at 250 kilometers per hour, which makes kind of a little bit of sense. One's going 200, one's going 150 in different directions, so they're both contributing a little bit to that. Alrighty, good question. All right, one more. Oh, this is a test question. A light is 15 feet above a sidewalk. Okay, we can see the lamppost there. Jill, who is 5 feet tall, is walking away from a point directly below the light at a speed of 6 feet per second. So Jill is walking away from this point that's directly below the light in that direction at 6 feet per second. Okay, how fast is Jill's shadow getting longer? Whoa, so Jill's shadow is out here, isn't it? If you think about where the light would shine on Jill, her shadow is going to be the length of this part right over here. So from this line right there to the end of that triangle. Okie dokie, how are we going to figure this out? All right, let's assign some variables. That's always a good idea with this stuff. So let's say Jill is going to be, I don't know, X meters away from the light at any given time. And let's say her shadow is going to be oh sorry, it's feet, not meters, but either way, her shadow is going to be s feet long. So we have two variables here. I know about how fast x is changing because they said Jill is moving at 6 feet per second. So the length of line x here is going to be increasing at a rate of 6 feet per second. The length of s, I don't know how fast that's increasing. All right, and that's all the information they give me except for Jill's height. So we've already seen a right triangle situation where we had to use Pythagorean theorem. But this is another common scenario that you get. And in this case, often when you have one triangle inside another, something that should immediately jump into your mind is similar triangles. So let's set up a similar triangle relationship here. I'm going to look at sort of the base of each triangle and the height. So the little triangle inside, its base is s, divided by its height is 5. And since that and the biggest triangle I can see are similar, then the base of the biggest triangle, which is x plus s, divided by 15, should be equal to that. Now we have a relationship between x and s, so we can find a relationship between their rates of change. Let's simplify first. Okay, so cross multiplying, I have 15 times s is 5x plus 5s. Oh, silly me for making up a problem that has 5's and s's in it. Okay, so this is an s here. And it's a mess too. So let's divide both sides by 5, and we get 3s equals x plus s. Okay, so subtracting s from both sides, I have 2s equals x. So now I can use my implicit differentiation. So differentiating both sides, on the left I get 2 times ds by dt is going to be equal to just dx by dt. Okay, so we were asked to find out what is ds by dt if dx by dt is 6. Well, that's going to be easy to do now. ds over dt will simply be equal to dx over dt, which is 6 divided by 2. So the shadow is getting longer at a rate of 3 feet per second. A little slower, in fact half as slow as Jill is walking. All right, good question. I like that one. All righty, let's move along. Here's the your turn question, and it's about a ladder that's leaning against a wall and sliding and stuff. Lots of fun things to consider with triangles in that one. And I'm going to flip to the solution for you. So if you want to pause, go ahead. Here's the solution, and there's a good diagram there to explain to you how all this stuff is working. And just take note about the negative sign there and what the fact that we have a negative rate of change means that something is actually decreasing in size, okay? So be careful with that when you're reading through all this. And let's highlight some of the key concepts here. So to solve a related rates problem, 4 steps. Find the mathematical relationship between the variables, the equation basically. Differentiate the equation implicitly with respect to time. Don't forget your chain rule. That's the most important part there. And determine any required yet unknown quantities, like we saw in our airplane problem, any other information we need to fill into that to help us out. And then we fill all that information into the differentiated equation and just solve for the required value. So that's an introduction to related rates. We've got a couple of more review sessions on those for some harder problems, but I hope that helped you with the basic concepts and with one type of related rates problem, those involving triangles. Happy studying, and if you have any questions, post them online.